Okay, my name is Ismael Ferrero. I'm a postdoc in the University of Oslo, the Institute of Theoretical Astrophysics. First of all, let me thanks the organizers for inviting me to give a talk today. It is always a pleasure for me to have a bit of my origins, and I hope next year we can meet all together in person in Córdoba. So for today, I'm gonna talk about a paper that is gonna be published actually this month on INA, and it's about the scaling relation of spiral and elliptical galaxies and how we can combine and understand the laws of this different type of galaxy in a simple and unique way. Okay, let's start it. So this is a work I did with Julio and Victoria, Mario, Jose, and Damian there in Córdoba during the past year, and as I say, it's going to be published this month on INI. I would like to give a short introduction about the scaling relation and the different property that spiral and elliptical types follow by separately. Okay, so 100 years ago, Hubble realized the real nature of galaxy, and he introduced the classification of galaxy based on their morphology, spiral and elliptical galaxy, and we all know this graph pretty well. Okay, and with the coming years after that, people have studied spiral and elliptical galaxy, and they have discovered many properties and scaling law this type of galaxy follow by separately. Okay, and the list is huge, and for each property or scaling law we find in a type of galaxy there is an antagonist in the other. Okay, so if a spiral galaxy are more in the field, the other are more in the cluster. The one have a young population of stars, the other have old, exponential, power law. So the list is huge. Okay, we have learned to study this galaxy as two different entities. Okay, and so the idea I want to transmit is that there exists a gap between these two kind of galaxy. That it started with morphology, with Hubble, and has extended to all kind of property. Okay, and with this work we try to bridge a gap between these two populations by studying or trying to merging the scaling relation that involve mass or luminosity, size, and velocity of the galaxies. Okay, so the key question here is why a spiral and elliptical obey different scaling law. Okay, so if we think in the space, in the 3D space that involve radius, mass, and velocity, we know all scaling law that there is different type of galaxy follow, and they are so important that all of them have, or most of them have, their own name. Okay, the Freeman law, commutative relation, Tully-Fisher, Fabre-Jackson, the fundamental plane, which of course it's a plane in this 3D space where the Fabre-Jackson is one of the projection. And again, I'm sure that most of you know them, but I would like to remind you which are these scaling law, or some of them. So basically, the Tully-Fisher relation, it's a correlation between the luminosity and the rotation velocity for a spiral galaxy. Okay, that tell you that the luminosity goes like v cube, like the velocity cube. Okay, and the antagonist for elliptical galaxies is the Faber-Jackson relation, not of course, because elliptical galaxies are supported by velocity dispersion. In this case, the relation is between luminosity and velocity dispersion. Sorry, but when I say early type galaxy, I mean elliptical galaxy. And when I say late type galaxy, I mean spiral. With times, this correlation have increased, of course, the number of observed galaxy, and the field now have lower uncertainties, okay, for both relation, okay, and of course we have the slope of the relation, which for the Tully-Fisher is 3 and for the Faber-Jackson is 4, but of course this value can change, okay. But many questions arose about this relation. One of the most important is about the scatter of the Tully-Fisher relation. And where does the scatter come from? Okay, because for a given velocity, so you take the vertical dashed line, for a given velocity, what gives this scatter in luminosity? And these correlations are important because allows to determine the distance of galaxy by measuring its rotation velocity, and from the fit I obtain the absolute luminosity, and with the apparent magnitude then I know the distance. Okay, so they are really important. So it's very important to have fits with the lowest uncertainties possible. Okay. And one important thing is that, of course, people try to see if there is a correlation with psi, if this scatter comes because all these galaxies with the same rotation velocity have different sizes, but no. A spiral galaxy, there is not a correlation of this property with radius, okay? But on the other hand, elliptical galaxy does, okay? There is a dependency with the radius in the Faber-Jackson relation. What it means? It means that for a given luminosity, if you take a luminosity, then the galaxy with the higher velocity dispersion are the smaller one, while the galaxy which the lowest velocity dispersion are the larger galaxy. Okay, so why there is a size dependency on the Faber-Jackson but not in the Tully-Fisher relation? Okay, so in the case of the Faber-Jackson relation for spiral galaxy, so both smaller and bigger galaxy follow the relation, the Faber-Jackson relation, but with different 0 points. Okay, so larger galaxy have a bigger 0 point here. Okay, so this dependency with the radius gives this dependency that you see in the equation inside the box, inside the plot, is that the dependency of the luminosity is not only with the velocity dispersion, instead it's also with the radius of the galaxy. So that is, as we know, was the fundamental plane. The big scatter in the Faber-Jackson came from the reason of not having realized of this dependency with the radius. Okay, so this was the origin of the fundamental plane, where one of the projection is the Faber-Jackson relation. But why this doesn't happen in the Tully-Fisher for a spiral galaxy? Okay. Again, of course, the values of this relation can change a bit from one author to another author, but it's not what we are trying to address here. Just that in general, these follow this fit with different slope, but they follow this relation. So people asked themselves, why is different from a spiral than for elliptical galaxy? What is the origin of this correlation? But why? I mean, there are many ways to explain this relation that people use the virial theorem or different, but you always need to take different ways to explain one or the other. Okay? And that is not clear and never was clear why I need to take different ways to get the Faber-Jackson or the Tully-Fisher relation. And that is what we wanted to answer on this project. And the way we try to answer it was by using cosmological simulation. Of course, I'm not going to introduce, because I'm sure most of you know the Eagle and the Illustris TNG hydrodynamical cosmological simulation. Okay, just that to tell that we use in both cases the cosmological box of 100 megaparsec which are very complete and include a wide range of physicist process. Okay, so the first things we did was to separate the sample of galaxies in early type, late type, and of course at the end we have some intermediate galaxies. We used only galaxy with stellar mass higher than 10 to the 10 in order to have a galaxy with an enough number of star particles, and have systems which are well resolved, and trust in the property we get from the particles. So we used to separate the sample, the two parameters. One is in the x is the gas fraction, and in the x is the kappa rod. Okay, so kappa rods tell you basically if the system is supported by rotation or if the system is supported by dispersion. We take into account both parameters in order to separate early type galaxy in red here and late type galaxy in blue, and gray are galaxy flagged as intermediate type. Here I'm showing Eagle on the left and TNG on the right. Okay, once we have the different type of galaxy in our sample, then we started by looking into the scaling relation of this galaxy. So for the case of the late type galaxy, here I'm showing the Tully-Fisher relation. So you can see that Eagle, which is in the top panel, shows like a higher scatter than the TNG, which is in the bottom panel. I am not going to discuss how well they reproduce observed results, because that is not the point I want to address. Okay, we want to understand difference between a spiral and an elliptical galaxy, and to do that, of course, we need to find a way to study them in a unique way. Okay, because here on the left, the blue are late type galaxy, which is the Tully-Fisher, and in red are the Faber-Jackson, so the early type galaxy. In one case we use the velocity dispersion, and in the other we use the circular velocity. Okay, and the way we try to unify was thinking or use the idea that for elliptical galaxy we measure the velocity dispersion in the line of the sea. So it is one component of the velocity, and we assume the other two are similar. Okay. And for a spiral galaxy, we measure the velocity dispersion, the velocity, while the other two components are almost zero. Okay. So if we multiply the velocity dispersion by square root of 3, you get this. Okay. So there are not practically difference between one or the other sample. It is like express both velocity in 3D. Okay, so what I'm saying is when we see these velocities, we can't distinguish early type and late type. Okay, but then we want to see the radius, and in this case it's not the same. Elliptical galaxy, as you can see, elliptical galaxy in red has systematically smaller radius. Okay, and so it tells us that for size the morphological type matter. Okay, I mean, when we talk about compare them with observation, eagle match spiral and TNG match elliptical in a better way. Okay, so why they have difference in size but not in velocity? So the first question we did is we made ourselves was, do they live in different halos? Because the difference in the size are huge. I mean, if you take a galaxy of 10 to the 10.5 solar masses, then there is an order of magnitude in radius. For example, for TNG, which is on the bottom. Okay, so regarding this question, do they live in different halos? Okay, we analyzed that, and what we found is that no, both type of galaxy lives almost in the same halos. Red, early type, blue, late type, and gray, which are the intermediate galaxy, live approximately in the same halos. Okay, there is a small difference. There is a small difference that, for example, early type galaxy lives like in more massive halo, but the difference is not as huge as we observe in radius. The black solid and dashed line you see in the plot are Monster and Beruzzi abundance matching relation, and none of them reproduce them for the extreme of massive galaxy. But of course, again, I am not focused on this. Okay, it was just to compare with some previous work. So in green, I'm showing an example. Imagine that you chose what happens if I take a halo of 10 to the 12 and I put on in a galaxy of 10 to the 10.5. Okay, so we create like a theoretical model. So this is the halo. You have dark matter halo of 10 to the 12, and then you put a galaxy of 10 to the 10.5 solar masses, okay? To model it, the rotation, the mass profile of the galaxy, then you need to assume effective radius for this galaxy, okay? So if you remember the plot where I showed the stellar mass as a function of the effective radius for TNG, I say that there is a one order of magnitude, for example, showed in that yellow shaded area, okay? So if I chose the most compact galaxy here, which is around 1 kiloparsec, 1 kpc, so I can put a galaxy of that size. Also I can put an extended galaxy, which the effective radius is around 10-12 kpc, or I can put different galaxies. Okay, so by choosing the halo, the galaxy mass, and the size of the galaxy, I can modulate the circular velocity curve of the different component. Okay, so in red here I am showing the dark matter halo. Of course here I am plotting just Navarro-French without the contraction, okay, just to make the plot more clear. But in our model we consider the contraction using the Egnedin model. And the blue correspond to the contribution of the star, and black are the total circular velocity. Okay, so let's go with the first case where we put a galaxy, a compact galaxy of 1 kpc of size. Okay, so in that case we are going to measure the velocity rotation of the galaxy in 1 kpc, and the velocity we are going to obtain is the one showed with the green circle. Okay, so it's absolutely dominated by baryons at this scale. Okay, for the case of an extended galaxy, of course with the same mass, in this case the velocity we measure is dominated by the contribution of the dark matter in that scale. Okay, and in the case we put a galaxy of an average size, like 4 kpc, which is almost like an average and normal size galaxy for that mass, we get a rotation curve which is almost flat, where both components contribute. Of course, the baryon contribute a bit more. Okay, and then of course we can do this exercise. We can do this exercise for a continuous size. Okay, and what we will get for the different size is the black line with the green dotted. Okay, so for size bigger than this brighter green point, we will get like the same velocity. Okay, and for size smaller than this brighter green point, what we call critical radius, there is a big dependency with radius, and the velocity increase a lot as smaller is the radius. Okay, so you can start now making an idea of this. Extended galaxy or bigger galaxy than this characteristical radius do not show velocity that depends with size. Okay, so Tully-Fisher not depend on size. Okay, I mentioned before that late type galaxies are more extended and have size which are most of the cases greater than this characteristical radius. But the Faber-Jacobson depend. Compact galaxy baryons import the size, and this is the main conclusion, of course, of the paper, and this is what is happening here. Okay, so we can repeat the same exercise not only for one beam of mass, but chosen 4 different beings with this color. And here I'm showing in log the velocity observed in the effective radius as a function of the effective radius, okay, for these 4 different beings. So for example, the blue line corresponds to a galaxy of 10 to the 10.1, where I am choosing different size, different effective radius for that galaxy, okay. So the blue solid line tell you the velocity you are going to measure in the effective radius if that galaxy of 10 to the 10.1 have that size of curve, and the halo mass chosen here to modulate the blue dotted point that correspond to the contribution of the dark matter is taken from the relation we observe in Eagle for the mass matching, for the stellar to halo mass relation, okay. So you can see that, I mean, simulation do not have to follow our so rudimentary model, but it works. If you can see, green points, for example, are a spiral on the right and elliptical are on the left, okay. So those galaxies that are on the right are in the flattest part of the course, so you are going to measure the same velocity, you won't have a dependency with the size, while the other galaxies are smaller and are in the steeper part of the curve will show a dependency with the size, okay. So it's the same for TNG. You can see that galaxies in that mass beam are distributed along the model, okay. So the model, we only need to assume a relation between the stellar mass and the halo mass. We need to modulate the contraction of the halo given the galaxy formation, which in this case we are using the Gnedin model, and that's it. It's a really simple model, okay. We can make some math here and see how this number ends in the Tully-Fisher or the Faber-Jackson relation, okay. So for example, for the delta we have in velocity, it's the mass, the difference in mass between these 4 model is 0.6, and then the difference in size we have is 1.2, and at the end you make some math and you got the fundamental plane there, okay. And in the case of the Tully-Fisher, we have the velocity, the delta in mass, and of course the delta in radius is infinite because the curve is flat, the curves are flat on that scales, so then you get the Tully-Fisher relation, okay. So it's a simple math that allow you to obtain the Tully-Fisher and the fundamental plane, okay. So fundamental plane and Tully-Fisher relation are just a reflection of the domain of baryons in the inner part of elliptical galaxy, which are smaller, okay, and the domain of dark matter halos in the outer part because the spiral are more extended, okay. And the bonus track we did, it was this secondary distance indicator, okay. So this is the same plot as before, but in this case in the x-axis I am plotting the softness brightness, okay, and that's because sigma instead of the radius. So in this way both axes are independent of the distance, okay. So and each curve here represent one of our model for different stellar mass, okay. So you can use this grid, and with this grid you can predict the stellar mass of the galaxy, okay. So you observe these 2 property. It doesn't matter if it's an early type, late type, you don't need to classify or to know that. Just put the values there and you interpolate between the different lines and you get the predicted stellar mass of the galaxy, okay. So in the plot I am showing the way x is the predicted stellar mass as a function of the real stellar mass that we know from the simulation, okay. And the results must agree very well with the real mass, and the scatter is good, it's really good. And And the scatter here is as competitive as the Tully-Fisher relation. And the important here is that until now, you have a galaxy and you need to know if it's early type or late type, because you need to know if you're going to use the Tully-Fisher or the Faber-Jackson as a distance indicator. But in this case, it doesn't matter. You just use this model, this grid, and you put any kind of galaxy and you get the stellar mass. Okay, and I will go quickly, but we did the same with some observation. We take Pisanio, Spark, Atlas 3D, and SLAG sample, early type and late type, and we did the same. You see, you can modify the velocity dispersion in order to analyze them with the same value of velocity. Okay, for the size is the same. There is an order of magnitude differences in size, and we plot for 3 different beings our model. Of course, there is more scatter because our observed galaxy and their property have bigger uncertainties. But points again follow the curves, and the argument works. Spiral are on the right and elliptical, and on spiral on the right and elliptical on the left. Okay, and that explains the dependency. Again, black line is the critical radius, this characteristical radius, where is defined as the radius where the contribution of the dark matter and the baryons in the Hall mass rate in the effective radius is the same. Okay, again, doing the same math, you can obtain the same relation with some different in the slope. Okay, again, the secondary distance indicator also works for observed galaxy, and we obtain a pretty competitive scatter in the predicted stellar mass for this observed galaxy. Okay, so the scatter we obtain here is even smaller or as competitive as the Tully-Fisher or the Faber-Jackson for this observed galaxy. And the advantage is that, as I said before, in this way I don't need to care about the morphology type of the galaxy. Okay, so the take-home measures I would like to give you is that Tully-Fisher and fundamental plane scaling relation emerge as a consequence of the depth difference where we measure the characteristical velocity of each type of galaxy. In one case, for a spiral galaxy, we are measuring the outer part where the contribution of dark matter is more important, and the curve, as our model shows, are flat, and that doesn't show a dependency with the radius. And in the case of elliptical, which are a smaller, more compact galaxy, we are measuring in the inner part where the baryonic part contribution is higher, and in that part of the galaxy, our model show a high dependency with the size of the galaxy. That give us the fundamental plane. And the second is that we can use this unified distance indicator that gives competitive result as using the Faber-Jackson or the Tully-Fisher, for which you need to know the morphology of the galaxy. And the plus of this one is that you don't need to care about the morphology of the galaxy. So thanks a lot, and you're more than welcome to read more in details the paper. Thanks.